Hello everyone. In this course, we will learn how to model a control system and how to perform a co-simulation with dynamic mechanical systems in addition to the basic control theory. In this course, we will use software called RecurDyn for the dynamic mechanical system and CoLink for the control system. Let me introduce you to the basics of the control system. There is a plant. This plant is a system we want to control or to influence its behavior. The input for this plant is an actuating signal, and the output is a control variable. These inputs and outputs are referred to differently depending on the industry. However, we generally call them plant input and plant output. The goal of control system is to figure out how to generate the appropriate actuating signal to produce the desired plant output, which is control variable. Therefore, the control engineer must generate the correct input for the system to achieve the desired output. At this time, desired output means target value. For example, the target values could be 100 m, which is the distance to be reached, or 25 degrees, which is the setting temperature of an air conditioner. In feedback control, the system output, which is plant output, is fed back. Here, the system's output means the control variable. And the difference from the current system is confirmed by comparing this feedback with the target value. For example, when a person travels to the destination, which is 50 meters away, the person is a plant. The distance traveled by the person is the control variable, and 50 meters, which is the distance to the destination, is the target value. The difference between the target value and control variable is the error term. If the target value is the same as the system output, the error will be 0. The goal of the control system is to make this error 0. Then, how do we convert this error term into an appropriate actuating signal, which is the plant input, to make error term 0? The answer is the controller that makes this possible. A controller is composed of complex control algorithms and devices and has come to be called a control system. In this lecture, you will learn how to build a control system using CoLink. You will define RecurDyn's nonlinear dynamic system as a plant and create a controller that makes the error term 0 through co-simulation with RecurDyn and CoLink. Now, let me introduce RecurDyn and CoLink. RecurDyn is dynamics analysis software that provides a fast and efficient solver, an intuitive interface, and various libraries. It supports not only dynamic analysis of rigid bodies, but also nonlinear flexible body analysis considering large deformation or contact, control analysis, and optimal design, as well as co-simulation with fluid, MPS, and granule, DEM, using particle method. CoLink is a block diagram-based control analysis program built into RecurDyn. Complex control systems, or hydraulic/electrical systems, can be modeled using various blocks provided by CoLink. By simulating the existing control model with RecurDyn's dynamic model, it is possible to perform an integrated analysis of firmware design, electrical and electronic design, and mechanical design. A lot of control systems are designed based on the linear control theory. However, the actual mechanical system is mostly nonlinear. The example you see here is a stacker system for loading large packages. On the left is the rigid body model. It seems that there is no difficulty in controlling. However, in reality, the large structure as shown on the right shakes and vibrates. In addition to that, the contact of the rail moving up and down occur, which means such nonlinearity is included in real world. In order to simulate such a mechanical system by including it in the control system, it should be expressed mathematically using a transfer function or a state space equation. However, it is difficult to build a mathematical model that takes into account nonlinearities such as vibration and contact caused by deformation, as mentioned above. In this case, if you use co-simulation of RecurDyn and CoLink, it allows you to easily include the complex nonlinear mechanical system in the linear control model and perform a control simulation without mathematical modeling of the dynamic system. In this time, after learning about the block diagram and response characteristic plot through a simple example, let me design a controller through CoLink and perform co-simulation with RecurDyn. This example is a control analysis model created by RecurDyn and CoLink. The green pendulum is slightly tilted to the right, and this control model makes it upright. Set the angle of the green pendulum measured from the vertical as a control variable value, plant output. Set the x direction translation force of the gray base body as an actuating signal, plant input. The goal is to make the green pendulum stand upright, and numerically, obtain the angle of the pendulum measured in the vertical direction to 0. Let me create this example model later in the session. For now, let's take a quick look. We will learn more about this example model in the practice video. Co-simulate the control model generated using CoLink with RecurDyn, and check the results in the plot. Then you will see that the target value is reached over time. Such a plot represents a response characteristic plot. The purpose of a control system is to generate an appropriate actuating signal for the desired output, and that means the error term becomes 0 in the end. As you have seen it from the previous example, the response characteristic plot is analyzed to judge these controllers numerically and qualitatively. Let's take a brief look at each term and its physical meaning for this response characteristic plot. Rising time, it means the amount of time for the system's response to reach from 10% to 90% of the target value, indicating the speed of response. The faster the rising time is, the more rapidly the intended value can be achieved, so that we can tell whether the controller is good or not. Peak time, it means the time taking for the output generated by the control input to increase to the maximum, which also means the speed of the controller response. Overshoot, if an excessive output occurs, it indicates the difference between the excessive output value and target value, which means that the response of the controller is appropriate. In the case of an electrical system, if electric current is higher than the electric current allowed by the system, we call it overshoot. The system may fail or shut down. Therefore, adjusting the overshoot to be acceptable by the system can also be one of the control goals. Settling time, it is the amount of time taking for the system's response to reach 98% of its target value. At this time, the response of the subsequent time must be within the 2% error range. It means the amount of time for control to literally end. Steady-state error, when there is no more changes in the response of the system, it indicates the difference between the target value and the system response, meaning that the response performance can be evaluated. The smaller the steady-state error is, the better the controller performs. Now, let's take a look at block diagram modeling. The method modeled with CoLink in the previous example is called block diagram modeling. According to the Laplace transform formula, arrange the differential and integral signals in series and configure to perform the 4 fundamental arithmetic operations. At this time, the line represents the signal flow, and various types of mathematical calculations are expressed through the block diagram. The block diagram you see now is the same as the one shown in the basic explanation of the control system earlier. If converting this to a standard feedback control system block diagram, it can be expressed as follows. Then, let's learn about each of the various elements used in the block diagram. GS is a plant or process, which is the system to be controlled. In general, the plant is constructed through mathematical modeling of the mechanical system. However, when performing a co-simulation with RecurDyn, the plant can be easily replaced with a RecurDyn model rather than a mathematical model. KS is a controller or compensator that generates an appropriate control input, that is, an actuating signal according to the error signal. PID controller can be a typical example. RS is a target value. The physical quantity for the target value is entered after defining the desired physical quantity by the controller designer. At this time, note that the physical quantity of the target value and GS, that is, the physical quantity fed back from the plant, must be in the same unit. DS means an interference signal generated by the plant. It mainly arises from irregular mechanical characteristics such as contact. In other words, this signal reduces the accuracy of the feedback signal. NS is an interference signal generated through the sensor. This signal does not occur in mathematical models, but it occurs very often in real systems, reducing the accuracy of the feedback signal. YS is a plant output value for the control variable from the system to be controlled. It is used as a feedback signal. ES represents the error signal caused by the difference between the target value RS and the final output value of the system. US is an output value from the controller. It is a control input transmitted to the target system, that is, an actuating signal. Let me introduce you to the user interface and basic functions of CoLink, which performs control system modeling. As mentioned earlier, CoLink is a block diagram-based control analysis program built into RecurDyn. I will show you how to do basic modeling related to the block diagrams and how to use various block functions. CoLink has the same UI layout as RecurDyn by default. The top part is a typical ribbon menu structure. Quick access toolbar and title bar showing the file name of a current model are located at the top. Below that is the ribbon menu. Functions in each tab are arranged according to the modeling process and convenience. Below the ribbon menu, the space where the modeling process performed is shown. It is possible to conveniently execute various block diagram modeling functions selected from the layout toolbar. On the right side, there is a database window where you can conveniently manage the values defined in the block. The actual block diagram is modeled in the working window. At the bottom, there is a status bar where you can check the progress of analysis after model is created. Now, let me explain the basic method of a block diagram modeling using CoLink. The block diagram modeling basically requires the creation, arrangement, and connection of blocks. Then, the model is completed by entering or modifying the parameters of the block. To create a block, click the desired block on the ribbon menu, and on the working window click once more to complete the block creation. To modify the parameters of a block, double-click the block or click the properties by right-clicking after selecting a block. There are two basic ways to connect the existing blocks. Firstly, this sharp part of the block is the output port. Click the output port of each block with the mouse and drag and drop it to the input port of another block. Secondly, after selecting a block, hold down the Control key and click another block to be connected. Then they are automatically connected by lines. When performing block diagram modeling, it sometimes happens that the same signal is input into the two or more blocks by dividing the signal. In this case, to connect multiple blocks, place the mouse cursor on the existing connection line. When the cursor shape changes to a plus shape, right-click to connect. Blocks can be simply moved by drag and drop, or the arrow keys on the keyboard. To efficiently align several blocks, use the alignment function. Now, you can select multiple blocks by mouse dragging and align them using the alignment function. Each tab in the CoLink ribbon menu provides various blocks for control systems modeling. Blocks are well categorized by type in each tab according to the block diagram modeling process. Let's find out what functions are grouped in each tab. The detailed function descriptions of the blocks provided in each tab will be explained in the next lecture. The CoLink tab menu contains screen control functions necessary for editing blocks in the working window or for overall modeling. It includes zoom in, zoom out, view translation in the working window, database window on, off, etc. Simulation tab includes functions related to simulation. It provides simulation start, stop, simulation-related parameter setting, etc. General tab consists of source block and output block. Source block generates electrical and mathematical signals and inputs them to other blocks. There is no input port, but only an output port. Output block are used to check the signal result generated through each block. You can export the signal result as a text file or check it as a graph through scope. Connector tab includes block elements for interworking with other systems, such as RecurDyn block, Simulink block, connection relationships between blocks and subsystem block. The representative block elements are demux and mux. Demux separates one input signal into multiple output signals, and mux combines multiple inputs into one array output. It provides the block elements that allows you to compose user-defined functions using C, Julia script, etc. Math tab provides blocks with both input and output port. It calculates the value and outputs the signal according to the function of each block using the input signal. Continuous and discrete tab consists of blocks for calculation of continuous and discontinuous functions. When performing co-simulation with RecurDyn, continuous blocks are mainly used since input to continuous functions is received. It includes state space block that expresses the motion equations of the system as state space equations and PID controller block. Toolkit tab provides blocks related to actuator or electric drives for mathematical models of motors, and blocks related to fuzzy that uses interface systems, FIS, files based on fuzzy theory. In this session, let me introduce you to the co-simulation of RecurDyn and CoLink. As mentioned earlier in the introduction to the control system, CoLink can solely perform a control system model simulation, or it can also perform a co-simulation with RecurDyn, which is dynamic analysis software. In the previous introduction to the basics of control, we learned that the actuating signal enters as plant input, and the control variables goes out as plant output. In this control course, we will use RecurDyn as a plant, that is, a dynamic system. Therefore, it is necessary to create plant inputs and plant outputs for the RecurDyn model as well. Based on this, how to perform a control simulation through co-simulation of RecurDyn and CoLink generally proceeds as follows. First, plant inputs and plant outputs must be defined in the RecurDyn model as mentioned above. It can be defined through the plant in /plantout functions in the CoLink tab in RecurDyn. Then, create the control system model in CoLink. At this time, add the RecurDyn block as plant to the control system, and connect the plant input and plant output appropriately to this RecurDyn block. Then, run a simulation in RecurDyn or CoLink. Let me show you a simple example according to the above process. First, create a plant input in the CoLink tab in RecurDyn. This plant input will be applied as an actuating signal of the system. In this example model, the x-direction translational force will be applied to the orange box below. Therefore, the x-direction translational force acting on the orange box is changed through the plant input, which is the actuating signal, input through the controller. Next, let me define plant output. The physical quantity measured from the RecurDyn model, that is, the control variable, will be the angle measured in the vertical direction of a green cylinder in this model. Therefore, the expression function is defined as plant output accordingly. Now, run CoLink to process the control system modeling. The block diagram modeling is done in advance, and RecurDyn will be added as a plant to connect them. Now it is time to perform a simulation finally. In the Simulation tab in CoLink, change the type to RecurDyn, and then start the simulation. When Connect is activated, co-simulation is performed even if the simulation is performed in either RecurDyn or CoLink. Since the control worked brilliantly, the green cylinder was successfully erected. We have learned the basics of how to perform co-simulation between RecurDyn and CoLink. In this session, let me introduce you to the main blocks provided by CoLink. As explained in the previous session, CoLink provides various blocks for modeling control systems. The General tab provides source and output related blocks. The Math tab provides blocks that perform various mathematical calculations using input signals and output them. The Connector tab provides blocks that define the connection relationship between blocks and blocks for co-simulation with other software. The Continuous and Discrete tab provides blocks for continuous and discontinuous function calculations. The Toolkit tab provides motor and fuzzy-related blocks. Let's take a look at the blocks in the General tab. The Source library in the General tab provides various blocks used as input values. The Output library provides various blocks used as output values. First of all, the chirp block in the Source library can output a sine curve that linearly increases the sine curve signal from the initial frequency to the desired frequency period. The relevant formula is as follows. In the parameters, the initial frequency, the target time to increase, and the final target frequency to be reached are entered. If you input parameters as mentioned above and check the result, you can confirm that a sine curve that increases linearly up to the specified frequency period is output as shown below. The first example is about the chirp block. Create a chirp block like this and connect it to the scope block to check the result. Set the initial frequency of the chirp block to 1 and the target time to 10. After setting the target frequency to 20, run the simulation. If you check the simulation results through the scope, you can confirm that the frequency is increasing linearly as much as the target frequency. This scope only shows up to 5 seconds, since the simulation time is set to 5 seconds. The clock block outputs simulation time as an output signal. The constant block outputs a user-defined constant value. A constant can be used as a parameter name defined in parametric value and working value rather than a number. It is also possible to define multiple values as outputs by using commas, in the constant block as shown below. When using each of these multiple output signals, the demux block can be used. Here is an example about the constant block. Create a constant block and input 10 as the constant value. After that, let's check with the scope. You can see that the plot of a scope is derived as a constant value of 10. If you have already defined the working value, which has the name of test, and value of 100, you can see that the constant value of 100 is applied even if you input it as test. Next is the step block. The step block outputs the result as a signal that changes in the form of steps. It follows the normal step function. One thing to note here is that RecurDyn obtains the Jacobian gradient during the calculation process. When using a general step function, this gradient cannot be obtained. Therefore, RecurDyn uses the step function in the form shown on the right. Numerical errors may occur if the step block in CoLink is used when performing a co-simulation with RecurDyn. Therefore, if you need to use a step signal when performing a co-simulation with RecurDyn, first create a step function through expression in RecurDyn. It is recommended to apply this as plant output and use it for modeling the CoLink control system. The sequence block outputs a repetitive signal according to the specific control points specified by the user. Input parameters consist of start signal, control time points, and output values. This block generates a periodic signal of the graph below and sends it out as an output signal. Let me show you an example of the step block. Create a step block and connect it to the scope to check the result as a plot. Enter the parameters for this step block like this. Enter the step time and initial value and final value. If you check the plot after the simulation, you can see such a step plot. If you compare it with the entered parameters, you can see that the step plot is drawn with a value of 1 when the step time is 1 second. Let's look at the sequence block. From this example, this block generates the output value, that is, a constant signal, for the control time point specified by the user in the constant sequence block. After changing it to the scope block, let me check the result as a plot. Let's take a look through the simulation. You can see the plot that periodically creates a signal of 0.1 for each constant control point entered previously. The signal chart block outputs a user-defined multi-step signal. There are 3 output methods as follows. In the case of the sensor type on the right, if the start signal is set to external, the signal chart can be operated when the input value is other than 0. Here is an example of signal chart block. You can compare the parameters of the signal chart block with the plot drawn through the draw button. When the type is time, the section time is input. The signal for that is inputted as well. The time is considered as the duration of the signal. Here it is maintained for 1 second, and then the signal of -1 is maintained for 1.5 seconds. After that, it keeps the signal as 0 for the last 2 seconds. In the case of the sequence type, each signal for the time is designated. When time is 0 seconds, a signal of 0 displayed. When time is 0.5 seconds, a signal of 1 displayed, and when time is 1, the signal is changed to 0. When time is 1.5 seconds, the signal changes back to -1. It changes to 0 again when time is 2 seconds. The sensor type defines a distinction standard for the input signal and outputs it accordingly. When the sensor type is applied, the input signal port is activated. In the Output library of the General tab, there are several main blocks provided. The to-file block to save time and input values as text files. The terminator block that do nothing. The stop block that stops the simulation when an input value other than 0 is entered. The scope block to view an input signal as a plot. The XY plot block that defines X and Y axes as desired values and displays them as plot. Here is an example using the scope and XY plot blocks among the output blocks. The scope block was mentioned earlier and can display a plot for the input signal. As you can see here, it receives the clock and constant signals and outputs them. In this example, there are 2 signals coming in. One is the blue line, which is simulation time, and the other is a plot of constant value. In the case of XY plot, the x-axis is defined as the simulation time of the clock block, and the output of the constant block is defined as the y-axis. Then, the constant values of 2 and 3 are set on the y-axis. The constant values of 2, 3 in the plot are shown, and the x-axis is set to simulation time. Next, let me introduce you to the blocks provided in the Connector tab. The Connector tab consists of block elements for connection between blocks, subsystems, and interworking with other systems such as RecurDyn and Simulink. The representative blocks related to connector are demux and mux. Demux branches one input signal into several output signals. Mux conversely combines multiple input signals into one output. At this time, the value outputs from mux are composed of an array. The next examples are about mux and demux. Mux allows you to group multiple values into one array. Since 3 values are inputted, the number of input port is changed to 3. The input signal is set in this order. Let me check the output with scope. Enter 1, 2, 3 like this. After these values are entered into an array, let's see how the array is drawn on the scope. Now, you can confirm that the constant values are outputted as 1, 2, 3 on the scope without any problem. In the case of demux, create a demux block and separate these array values with demux, which were previously grouped with mux. For your reference, the 3 values were grouped earlier. Let's check the 2 outputs separated through the demux block. If you run the simulation and check each plot, you can see the constant values of 1 and 2. As you see here is that the first and second values out of the initial 3 input values are output. Subsystem makes it possible to manage some parts of the CoLink model by grouping them into a single block. By double-clicking on the subsystem block, you can enter the subsystem mode and model the control system. Also, the number of inputs and outputs can be added through the dummy block menu in the pop-up menu. The RecurDyn block is used to simulate the RecurDyn model and the CoLink model together, and the plant input and plant output defined in RecurDyn are used. The Simulink block allows you to perform the co-simulation with Simulink of MATLAB, and this block creates an M file to perform a co-simulation. The RecurDyn block is used as a plant in the control model, and the plant inputs and outputs are defined. This example is about PID controller. RecurDyn, as a plant, is connected to the plant input and plant output. Then, the plant input and plant output set in RecurDyn will be applied, so that the co-simulation can be performed between RecurDyn and CoLink. Among the blocks provided in the Connector tab, the features related to user-defined functions include user function, expression, C function, and Julia function. User function allows you to directly define the desired function block by using various functions provided by CoLink. The star.dll file can be directly created to define the block, and a separate external compiler is required to generate this DLL. Expression is used when using simple formulas. You can also use arithmetic operations and formulas defined in math.h in C++. CoLink's expression uses Julia script. C function can be utilized by using the DLL file with code written in C or Julia. Julia function can be used by directly inputting Julia script in the dialog box displayed when double-clicking the block. So far, we have learned about the blocks related to the Connector tab. The following are the blocks in the Math tab. It consists of block elements that can perform various mathematical and logical operations, and block elements for nonlinear systems. First, the gain block multiplies the input value by the gain value specified by the user. The sum block outputs the total sum as an output signal by performing addition or subtraction operations according to the plus or signs on the values coming in as input signals. The logical operator block performs logical operations such as AND, OR, and NOT on input values. Then, let me show an example using the gain block and sum block. In the case of gain blocks, as described above, the value entered in gain is multiplied. In the example, I entered 5 for the constant value. 4 is entered in gain. Then, the multiplication of 5 and 4 should be drawn on the scope. Here, you can see that 20 is drawn on the scope like this. The following example is about the sum block. First, create a sum block. Let me model the cosine and sine, so that the sum of the values of these two plots are output. Let me check what the original sine and cosine values are. Run the simulation to obtain the results. Now you can confirm that the sine curve looks normal like this. You can see that the cosine curve looks normal like this. The values of these two plots are combined and create a plot like this. Relational operator block calculates the correlation between two input signals and returns 1 when true and 0 when false as an output signal. Refer to the table below for the types of correlation. The following are math function, sine, and limiter blocks. The math function block returns the result obtained by performing mathematical operations, such as exp and log on the input value as an output signal. The sign block changes the sign of the input value. The limiter block sets the limit value of the input value, and upper/lower values can be defined. It is mainly used to define limited torque, current and voltage capacity. This is an example of the limiter block. This example is made in advance. If the sign signal is generated through the sign block, you can check the sign plot with the maximum value of 1 and the minimum value of -1. The upper limit is set to 0.5 on this limiter block. When this limit is applied, the maximum value is 0.5. The rest of the top part is cut off. Let me compare this with the original sine curve. When comparing, you can see the part where the value is limited to 0.5 in the graph on the left. The relay block allows you to directly designate the output value when the size of input signal is larger or smaller than the defined value. Relay on-off is determined according to the switch on-off points of input signal. If relay operates, the output value outputs the value defined in output when on until relay does not operate. If relay does not operate, the value defined in output when off is output until relay starts operating. The switch block designates a total of 3 input signals. The switch block determines whether the specified standard is satisfied with respect to the second input value among input signals. If it is satisfied, the first input value is output, and if not satisfied, the third input value is output. Next, we will learn about the blocks for calculating continuous and discontinuous functions. The delay block normally outputs the input signal after delaying the output value specified by the user in time. The next one is a delay block example. First, create a sign block. A sign signal is generated through the sign block, and you can normally check the graph plot for the sign signal. Let me apply delay. Let me set delay to 1. If you check the scope plot after the simulation, you can see the delay of 1 second is generated for the original sign signal before the sign signal starts. Now, here are the blocks for differentiation and integration. Differential and integral values are output for each input signal. In the case of differentiation, instability may occur due to its characteristics when performing co-simulation with a dynamic mechanical system in RecurDyn. In particular, in the case of a complex nonlinear dynamic system, numerical errors may occur when a differential value is used as a plant input. Therefore, it is not a good idea to use a differential block in this case. Instead, it is recommended to output the differential control variable such as speed as a plant output in RecurDyn so that it can be used in the CoLink controller. In addition, the equation of state for continuous functions, transfer functions, and PID controller blocks are provided. The same discretized equation of state, transfer function, and PID controller are provided for discontinuous functions. It also provides discrete filter block that provides infinite impulse response, IIR, and discrete time integrator block. So far, the blocks related to continuous/discontinuous functions have been introduced. Lastly, let me explain the blocks provided in the Toolkit tab. The Toolkit tab provides the blocks for mathematical models of actuator, electric drive, and fuzzy. Particularly, in the case of actuators and electric drives, they are divided according to the existence or non-existence of a controller. If there is no controller in the motor input part, and the motor system is only modeled, PMDC, DC, and PMSM motors in the actuator tab are used. Electric drives are used when the motor and the controller are considered together. The fuzzy block is also provided, allowing you to use FIS, fuzzy inference systems, file based on the fuzzy theory. Let me introduce you to the co-simulation between RecurDyn and Simulink in this session. The process is basically similar to the co-simulation with CoLink. Plant input and plant output are defined in the RecurDyn model and connected to the Simulink control system through the RecurDyn block. You can perform the simulation either in RecurDyn or in Simulink. First, let's learn about the basics of co-simulation between RecurDyn and Simulink. The diagram you see here shows how the co-simulate is performed between two programs. First, RecurDyn calls Simulink through the previously created shared memory. Second, RecurDyn transmits the plant output values to Simulink through the RecurDyn block in Simulink. Third, after receiving the plant output values sent from RecurDyn, the control analysis is performed in Simulink. The derived motion signal, that is, the plant input, is transmitted back to RecurDyn through the shared memory. How the co-simulation is performed is to repeat this process. What do you think is the difference between the host and the client when performing co-simulation between two programs? Let me explain the differences using RecurDyn and Simulink as examples. If RecurDyn is specified as the host program and a RecurDyn model is simulated, RecurDyn calls Simulink for execution and simulation. The simulation time should be specified in the host. Each of linked RecurDyn and Simulink models is controlled through the host, RecurDyn. Therefore, in case of stopping or terminating the simulation, it must be controlled in the host program. Conversely, if Simulink, which is an external software, is specified as the host, the simulation is executed in Simulink or RecurDyn is called to proceed with the co-simulation. When the host is Simulink, RecurDyn is already running, and when the model is activated, this RecurDyn analysis model is called, and the co-simulation is performed. When the host is Simulink, RecurDyn has already executed. When a model is activated, this RecurDyn simulation model is called, and co-simulation is finally performed. Now, let's look at the compatibility of each version of RecurDyn and Simulink. RecurDyn provides two functions that can perform co-simulation with Simulink, which are CoSim Simulink and General CoSim. For each function, the compatibility of RecurDyn and Simulink by version is shown as in this table. Don't forget to check the version in the table carefully and perform the co-simulation according to the version of each program on your computer. There is an M file that plays an important role in the co-simulation process of RecurDyn and Simulink. A RecurDyn plant block should be created within Simulink for the co-simulation of RecurDyn and Simulink. At this time, the RecurDyn block is created through the M file, which is a MATLAB script file in which RecurDyn model information is stored. When RecurDyn is the host, it automatically runs MATLAB to perform the simulation. Next, let me introduce you to each setting item of the Simulink interface that needs to be set for the co-simulation with Simulink in RecurDyn. The two functions for the co-simulation between RecurDyn and Simulink, which are CoSim Simulink and General CoSim, introduced earlier, consist mostly of the same setting items. In this lecture, let me explain about General CoSim. First, click the General Plant Input or General Plant Output icons to create or delete them. For reference, in the case of General Plant Output, it is created using RecurDyn expression. Click the GCoSim icon to display the General CoSim dialog box shown on the left below. Select the type as Simulink and specify the plant input and plant output previously created through General Plant Input and General Plant Output on the left side of the GCoSim icon to PIN and POut. If you click the button in the CoSim section, the dialog box shown on the right is opened. Master program literally means to specify the host program in the co-simulation. Basically, either RecurDyn or Simulink is selected. If RecurDyn is selected as a host, Simulink is automatically set as a client and vice versa. Plant file name is the name of the RecurDyn model file that becomes the plant in the co-simulation. Interface time step means the period between two programs to send and receive data. This interface time step must be greater than or equal to the maximum time step of the RecurDyn model. If the interface time step is less than the maximum time step of RecurDyn, the simulation proceeds by automatically reducing the maximum time step to be the same as the interface time step. In general, if the controller sensitivity is low and only a rigid body model is included, it is recommended to define the step as 0.001 seconds. If a flexible body is included, it is recommended to define the step between 0.0001 and 0.00001 seconds. Waiting time is applied only when RecurDyn is the host program and is the time RecurDyn waits for Simulink response. In relation to this, when performing a co-simulation between RecurDyn and Simulink, an error stating the client program does not respond may occur. This error occurs when there is no response from Simulink within the time set by waiting time. If your PC is very slow or it takes a long time for Simulink to calculate, not sending a response within the period set by waiting time, you should extend waiting time or check the modeling error in the Simulink. Next are the Create a Plant block items. Output file name allows to specify the name of the simulation result file. In the case of RecurDyn host, the same applies to output file name of the dynamic kinematic analysis dialog box in the Analysis tab. In the case of Simulink host, define the name of the result file. Note that all file names and paths related to the co-simulation between RecurDyn and Simulink can only be written in English or numbers. The mfile to create plant block function creates an mfile required to add a RecurDyn block as a plant to the control model of Simulink. Mfile is created in the working folder where the RecurDyn model file is located through the export button. In Simulink, the RecurDyn block is created by executing this mfile and entering a dedicated command. In this case, enter grd-host as a command when RecurDyn is the host program and enter grd-client when Simulink is the host program. This will be explained later with an example. The following items are related to run Simulink model in order to execute Simulink. MATLAB program sets the path of matlab.exe to run MATLAB when RecurDyn is the host. Usually, if you check the MATLAB installation path, you can see that there are two matlab.exe files. It is recommended to define matlab.exe in the Win64 folder in the bin folder. As I mentioned before, please note that only English and numbers can be used in both file and path names. Mfile to run Simulink model literally creates an mfile to execute MATLAB Simulink. It can be created through the export button and co-simulation can be also performed automatically just by executing this mfile. Run Simulink model specifies the Simulink file created by the user, that is, an MDL file or an SLX file. Next, let me explain the actual co-simulation process through the examples. This example was briefly shown when explaining the response characteristic plot earlier. Hope you remember what I am talking about. You can see the green pendulum is slightly tilted to the right. This is a control model that makes it upright like this way. Set the angle of the green pendulum measured from the vertical as the control variable, plant output. And the x direction translation force of the gray base body is set as the motion signal, plant input. The goal is to make the green pendulum upright, which means, numerically, it is to make the angle of the pendulum measured from the vertical direction to 0. In this example, the PID controller is modeled in Simulink, and the co-simulation is performed by applying RecurDyn as a plant. First, let me explain how the plant input and plant output are specified in the RecurDyn model. After creating a plant input, this is applied to GPIN function when creating an expression. The created expression is applied as the x direction force of the translational force to the gray body. The angle of the pendulum measured from the vertical direction applied as general plant output was defined as expression by creating general plant output. The expression function used in this case uses the function that returns the rotation angle psi corresponding to the first rotation order of zxz Euler angle. For reference, another value defined as general plant output is the rotational angular velocity of the pendulum. This corresponds to the differential control in the PID control. If the control system differentiates the rotation angle measured in RecurDyn, the value is missing due to the differential characteristics. As a result, an error occurs in the dynamics analysis. Therefore, if the rotation angular velocity value accurately measured in RecurDyn is brought to the general plant output and used for differential control as it is possible to perform an accurate dynamics system control. Finally, all general plant outputs are defined. Now, let's look at an example using RecurDyn's general CoSim with Simulink interface. First, this case is about the co-simulation procedure when RecurDyn is the host program. In general CoSim, it is necessary to define plant input and plant output using gPlantIn and gPlantOut. Create plant input using the add button in the gPlantIn function and define gPlantOut using the same expression function as in the previous example. In the same way, define gPlantIn as the x-direction force of the translation force of the gray base body. Please note that the expression function must use the gPIN function as a dedicated feature to the general CoSim. Then, click the gCoSim icon and create a CoSim environment using the Add button. Change type to Simulink and click the Add button after clicking each PIN and POut item to automatically import the gPlantIn and gPlantOut created earlier. Now, click the button of the CoSim to set the Simulink interface items. As explained earlier, since the setting items are the same as CoSim Simulink, let me skip the description of each item and create an M file. Since this example represents RecurDyn as a host program, two M files are created for RecurDyn plant block generation and Simulink execution. Now run MATLAB. Set the MATLAB working folder to the working folder where the RecurDyn model is located. Execute the M file that was created earlier for the RecurDyn block creation. Then input the command to create the RecurDyn block. In this example, the general CoSim function is used and RecurDyn is the host. Enter the command grdhost and press enter. Then you can see that a RecurDyn block has been created. Open the SLX file, which is an existing Simulink model file, by double-clicking. After that, drag and drop the RecurDyn block to the plant block for connection. After saving the Simulink model, exit MATLAB. Now that RecurDyn is the host, run the simulation in RecurDyn. Then, MATLAB is automatically executed and the co-simulation is performed. You can see that the green pendulum is well controlled to stand upright in the resulting animation. We will now briefly learn the co-simulation procedure using general CoSim when Simulink is the host. The setup process is the same as when RecurDyn is the host. Change Simulink to host in the CoSim settings to create an M file. After saving the M file, exit RecurDyn and execute MATLAB to run the M file. In this example, the general CoSim function is used and Simulink is the host. Enter the command grdeclineIt to create the RecurDyn block. Now, open the Simulink model file and connect the RecurDyn block to the plant by dragging and dropping. After double-clicking the RecurDyn block and the inside red Dynamics model block to change step to 200 the same as RecurDyn, exit to the top level. Then close RecurDyn. Check the simulation time and run the simulation. Since Simulink is the host, the simulation is performed in Simulink, and RecurDyn automatically runs the simulation. When the simulation is complete, you can see that the pendulum erection is controlled. We have learned how to co-simulate between RecurDyn and Simulink so far. Thank you, and that's it for today.